Hi one and all. In this video, we shall learn how to write the Verilog hardware description language code for mod 8 up counter. More specifically, we shall see how we can able to use Xilinx design suite in order to simulate and verify the working of mod 8 up counter. Clear? So before jumping into VHDL code, first we shall have a brief introduction about what is mod 8 up counter means. We shall understand that first, and then after that we shall see how we can able to write the VHDL code for mod 8 up counter. Clear? Okay. See, first and foremost, as the name itself says, mod 8 up counter is basically a counter, right? You may have heard the word called a counter, which usually will count, is used to count for a sequence, right? Correct? And now we shall see what is actually mod 8 counter means first, and then we shall see what is actually mod 8 up counter means, right? Okay, mod 8 counter is the one, as the name itself says, is a counter which can count up to 8 states. For example, let us assume 0 is the initial state, okay, and 1 is the next state, 2 is the next state to 1 state, then 3, similarly 4, 5, 6, 7. Okay, 0 is the initial state. Okay, 1 is the next state to the 0th state. 2 is the next state for state 1. Similarly, 3 is the next state for 2. 4, 5, okay, 6, 7. So totally, if you count, how many number of states are there? 1, 2, 3, 4, 5, 6, 7, 8. So if a counter has totally 8 states, then it is called as a mod 8 counter. In case of mod 4 counter, totally it will have 4 number of states. Like for example, 0, 0, 1, 2, 3, again 0. So this is mod 4 counter. Clear? Okay, we understood what actually mod 8 counter means. Now we shall see what is actually mod 8 up counter means. As the name itself says, mod 8 up counter means that is a counter which will count the sequence in an upper order, like 0 to 1 and 1 to 2, then 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, then 7 to 8. We call this type of counter as an mod 8 up counter, whereas there is one more type of counter is called down counter. Okay, it's actually reverse of up counter, which will count in a reverse order, like 7 to 6, 5, 4, 3, 2, 1, 0, 7, 6, 5, 4, 3, 2, 1, 0, like that. That is a down counter. But here our requirement is we need to design mod 8 up counter, means we need a counter which looks like this. Clear? Okay, so one more basic point that you need to remember here is usually counter will be designed by using the flip-flops. Why? Basically the reason is simple. If you want to go to the next state from the present state, this present state should be known, right? Or in other words, it should be saved in the memory element, right? Then you can fetch the current state from the memory element, and then you can go to the next state, right? So, and we already know that flip-flops can act like a memory element, right? And hence remember, whether you design up counter or down counter or mod 3, mod 4, mod 8 counter, you need a flip-flops. Now the next interesting question is, how many number of flip-flops is needed? So actually flip-flop is a memory element which can store only 1 bit, right? But to design the counter, as I said, the flip-flops are used. But one more piece of information which is very important is how many number of flip-flops you need. That is an important point that you need to address before jumping into the actual design of the counter. Clear? So it is very simple to find out the number of flip-flops required for designing the counter. Just look at the maximum state that a counter can reach. So in case of mod 8 up counter, this is the maximum state or the upper state, maximum state, or in other words, you can understand that as an upper state, and we can treat 0 as the lower state. Okay, just see the upper state, and the state has a value 7, right? And to represent this 7, I mean decimal value 7, how many number of bits is necessary or is needed? it is 3, right? So 7 can be represented in binary like this. 111 in binary is actually 7 in decimal. So how many number of bits is needed to represent this upper state? 7 in this case. It is 3, right? And hence you need 3 flip-flops, 3 number of flip-flops to design mod 8 up counter. So similarly, if you are required or if you are asked to design mod 4 counter, okay, mod 4 counter, so 0th state is the lowest state, 1 2 3, and 3 will be the upper state, right? And how many number of bits is needed to represent the upper state? It is only 2, right? 1 is nothing but 3. So in this case you need only 2 number of flip-flops to design mod 4 up counter or down counter. Clear? Okay, now we understood how many number of, or how to find how many number of flip-flops is needed to design the counter, right? So this is very important. Clear? I will come back to this why it is important. Now we shall understand the operation of mod 8 up counter at a high level. So let us assume we are in the 0th state. This is the current state or in the present state. Now how the counter will work is, if you apply the clock here, now, then the counter will be triggered from present state to the next state. I mean, it will jump from 0 to 1. Again if you apply the clock, it will jump from 1 to 2. Again if you apply the clock, then it will jump from 2 to 3. So like this it will work. And if 7 is the present state of the counter, and if you apply the clock, then it will jump into 0th state. So this is how the counter will work. So this information acts like fundamentals to understand how to write the VHDL code. So I already mentioned before starting VHDL code, we should have a brief information about the circuit, and then you should go about the port descriptions. These are very important, and then you should go to the code, right? So as I said, we need clock here because only on the application of the clock it will the counter will trigger to the next state. So instead of CLK, we have used C here. You can use CLK also, no problem. C stands for clock in this case, which is actually input, and R stands for reset. So as I already told you what is the use of reset in the previous videos itself. Again here reset pin is used for our convenience to start the counter with an initial state 0. That's it. Okay, and Q is actually our counter. Q is actually our mod 8 up counter. And how many number of flip-flops is necessary here? 3, right? And hence Q should be a vector. It's actually a vector here. It should be a vector, okay, of size 2 down to 0. Why it is 2 down to 0? Because we need 3 flip-flops. Clear? And I will tell you interesting thing is, here Q is actually in and out. It is not only in, it is not only out, it is actually in and out. I will tell you the reason why it should be in and out in this case. Clear with this? Okay. Now we shall go to the core part. As I already told you, flip-flops are used to design the counters, right? So, and I already told you in the last class, whenever a flip-flop come into picture, while writing the VHDL code, you should remember that you should use a construct called process, right? Okay, I have already explained the syntax of process in the previous video. So again, I no need to explain the syntax here. Okay, and I already told you what is the purpose of C as a parameter here, R as a parameter here. Now directly we shall jump into the logic. See here. Okay, for better clarity, I will remove this. See here. What this indicates, if reset is applied, if you apply the reset, then actually the counter or what I can say, counter will have the value 0. So you see here, since you are dealing with multiple bits here, that has to be enclosed within double quotes. Clear? So 0 0 0, it is in binary. Actually the decimal equivalent of 0 0 0 is 0. Means you are initially when you apply the reset, you are making the counter to stay in 0th state. Clear? 0th state. Understood? Then if you apply the clock, C is equal to 1 means when you apply the clock, counter should jump from present state present state plus 1, I mean present state to the next state. Clear? Clear means if 0 is a present state, when you apply the clock, it should jump into the next state, which is 1. Clear? And this repeats whenever you apply the clock. That is how this piece of code will work. Okay, interesting thing is here you are using q towards the right side of this assignment operator, right, as well as you are using q towards left of the assignment operator, right. And moreover, you already have familiar this when C also. If you are using the variable, let us say A is a variable and B is a variable. Now you are assigning the value of A to B like this in C or in C++ or in Java. I can say A here is used for reading purpose, right? Means it will fetch the content of A from the memory. Okay, and then that content will be returned to B. Means I can say if you use the variables towards right side of the assignment operator, then I can say it is used for reading purpose. Similarly, if you use the variables here B in this case, left side of the assignment operator, then I can say that variable is used for writing purpose. Clear? Similarly here, with that understanding, q has been used here, I mean towards the right side of the assignment operator. This is the assignment operator in VHDL case, and q is also used towards left of the assignment operator. Hence q should be defined as both input and output. Clear? Okay, so I hope we reached the end of the theory part. Okay, now we shall try to simulate this using the tool. Okay, now in order to save the time directly, I have already launched the tool. Okay, so as usual, start with a new project. Okay, you can give the name of the project as mod 8 up counter. Okay, then next, every project should have a new source file, and the type of that file should be a VHDL. Okay, next, and here I need clock, I need reset, I need the counter. Q should be in and out. This is important, and it should be a bus, I mean a vector of dimension 3, totally 3, 0 to 2. Clock a single bit input, reset is a single bit input. Clear? Finish. Next, finish, and automatically the IDE or the tool will generate the code. Okay, and your job is you need to write the code between this begin and end of the module. So again here what you have to use, which construct that you have to use is process, because you are dealing with the flip-flops, and clock and reset are the parameters, and process should begin with a keyword called begin. Okay, and it should end with a keyword called end process, and it should be terminated with semicolon. Clear? Okay, now we shall write the main logic here. If reset is applied, I mean if reset is 1, then what you have to do, then counter should have the value, okay, 0 0 0. Since I am dealing with multiple bits, I am enclosing with in double quote. Else if, otherwise, I mean else check whether clock has been, not CLK here, see here, clock has been applied, I mean 1, clock is 1. Okay, if clock is applied, then what should the counter has to do? Counter q should be assigned with the value of present state plus 1, so that q will go to the next state. Clear? Then this if block should be ended with the keyword called end if, and end that statement with semicolon. Clear? So this will be the logic for mod 8 up counter. So now as usual, after writing the code, save your work, go to implement design, go to synthesize, and call for check syntax. So now syntax has been checked successfully. Go to simulation part, go to project, go to new source, and choose test bench waveform. Then you give the name for the waveform as W, and click next, finish, and again click finish. Okay, now this is interesting. See here, this is the clock. We can't able to change the value of the clock, it is predefined, and this is our counter. Okay, Q is our counter, and as usual, similar to positive edge trigger D flip-flop, reset should be set to high initially, then completely low. Clear? Okay, we shall save the waveform. This is our waveform. Go to process, go to simulator, and simulate the behavioral model. We shall see. Okay, interesting. See here, as per the code, if reset is 1, then counter should have the value 0, right? See here, that's what here it is happening. If reset at this point, reset R is 1, so hence our counter will have the value 0. And when you apply the clock, see, this is the positive edge of the clock, correct, approximately, and now the counter is changing from present state to the next state, 1. And again, when you apply the second clock, it is changing from 1 to 2, again 2 to 3, 3 to 4, 4 to 5. But here we can't able to see the complete cycle, right? I can't able to view after 5 whether I am getting 6 or not, right? So to do that, okay, close this. Okay, you no need to save that. Okay, or save, close that, click by yes. I will choose a new source, I mean test bench waveform. Okay, I will give the name as new waveform or new wave. Okay, there should not be a space. New wave. Click next, finish. Here, this is important now. This is important. Now, change this clock high time to 50 and clock low time to 50. Means we are just compacting the clock. Clock high means from here to here. Low means from here to here. This is positive. This is negative cycle. Clear? This is what I was telling about delay. Don't worry about this in depth now. So just I am compacting. I am making this clock cycle a little bit compact way. Clear? Click finish. Now see here, you will understand clearly now. Now previously, see here, the clock duration was wide, correct? Now look at the new waveform, it has been compacted. That's what we did. Clear? So just set the clock high time to 50, low time to 50, and as usual reset high, then low, then save your work. This is your new waveform. Now you want to simulate this new waveform, select that, go to process, then call for simulate behavioral model. Now interesting, see here, as usual, the counter is starting from 0th state. When you apply the clock, it is going from 0 to 1, then 1 to 2, 2 to 3, again 4, 5, 6, 7. Interesting, after 7, when you apply again the clock, it is going to 0th state. So this is what we call it an mod 8 up counter. Clear? So this concludes this session where we understood the operation of mod 8 up counter, and we simulated and verified the working of mod 8 up counter using our design suite. Clear? So thank you, Nendo.